When I started in data science, I was overwhelmed by the endless techniques and algorithms. It wasn't until a mentor showed me the 5 statistical principles we're covering today that things finally clicked for me. These concepts transformed how I approach every data problem. Instead of jumping between trendy techniques, I now start with these core statistical foundations that solve most challenges. Today, I'm sharing this framework that's helped me and countless other data professionals work more effectively. The 80-20 rule of statistical concepts. What if I told you that just 5 statistical concepts power 80% of data science work? When most people start learning statistics for data science, they're confronted with an overwhelming landscape of techniques. Textbooks present dozens of statistical tests, probability distributions, modeling approaches, and specialized methods. Online courses promise to teach you everything from basic t-tests to advanced time series analysis. The sheer volume of statistical knowledge seems impossible to master. This overwhelming array of options creates a common problem for beginners: analysis paralysis. When faced with a new dataset, they freeze, unsure which of the dozens of techniques they've heard about might be appropriate. Should they use ANOVA or chi-square? Is this a case for logistic regression or decision trees? The statistical toolbox seems to expand endlessly, with each tool requiring its own set of assumptions and interpretation guidelines. But here's what's fascinating. When you observe experienced data scientists at work, you notice something surprising. Despite having knowledge of many advanced techniques, they spend most of their time applying a small core set of statistical concepts. They don't jump to the most complex method available. Instead, they rely on fundamental statistical thinking principles that serve as the foundation for almost all data analysis work. This pattern follows what's known as the Pareto principle, or the 80-20 rule, named after economist Vilfredo Pareto, who observed that roughly 80% of effects come from 20% of causes. This principle appears repeatedly across many fields. In statistics and data science, it suggests that about 80% of your analytical results will come from mastering just 20% of available statistical techniques. What's particularly interesting is how this principle manifests in the development of expertise. A study of experienced data scientists revealed that they prioritize mastering a handful of core statistical concepts rather than attempting to learn every available technique. This approach aligns perfectly with the Pareto principle. They recognize that a limited set of well-understood tools can yield the majority of valuable insights in data science. But which statistical concepts provide this outsized impact? Research points to 5 fundamental areas that form the backbone of effective statistical thinking: descriptive statistics, inferential methods, probability, Bayesian thinking, and regression analysis. These core concepts appear repeatedly across different domains and applications in data science. Let's consider why these 5 concepts have such universal importance. Descriptive statistics helps you understand what your data actually contains, the central tendencies, the spread, the shape of distributions. This foundation is essential before any further analysis can begin. Without a solid grasp of what your data actually shows, any advanced technique will be built on shaky ground. Inferential statistics allows you to make decisions based on samples rather than entire populations. This is crucial because in most real-world scenarios, we can't observe every possible data point. Inferential methods provide the framework for making reliable generalizations from limited observations, a fundamental need in almost any analytical work. Probability serves as the language of uncertainty, which is unavoidable in any real-world data analysis. Understanding probability helps you quantify the likelihood of different outcomes and recognize the role of chance in observed patterns. This prevents you from mistaking random fluctuations for meaningful signals, a common pitfall for analysts without strong statistical thinking. Bayesian thinking provides a powerful framework for updating beliefs as new evidence arrives. This approach mirrors how humans naturally reason and allows for the formal incorporation of prior knowledge into statistical analysis. In practical terms, it helps you make better decisions when information is incomplete or evolving, a constant reality in data-driven decision-making. Finally, regression analysis offers a versatile approach for understanding relationships between variables and making predictions. Its flexibility allows it to serve as both an exploratory and predictive tool across countless applications, from business forecasting to scientific research. What makes these 5 concepts particularly powerful is that they form an integrated system of statistical thinking rather than functioning as isolated techniques. Descriptive statistics informs what patterns might exist in your data. Probability helps you understand when those patterns might be due to chance. Inferential methods help you determine if sample patterns likely extend to the broader population. Bayesian thinking allows you to incorporate prior knowledge and update your conclusions as new data arrives. And regression provides a framework for modeling relationships between variables. When you understand these concepts as an interconnected system, you begin to see the same fundamental statistical patterns appearing across seemingly different data challenges. A retail analyst examining customer purchase behavior, a healthcare researcher studying treatment outcomes, and a financial analyst evaluating investment returns are all applying variations of the same core statistical thinking, just in different contexts. Consider a few examples of how these core concepts solve problems across domains. In marketing, descriptive statistics reveals customer segments, inferential methods test if marketing campaigns truly increase sales. Probability models predict customer behaviors. Bayesian approaches update targeting strategies as new data arrives. And regression identifies which factors most influence purchase decisions. In healthcare, these same concepts help summarize patient outcomes, determine if treatments show significant benefits, calculate risk probabilities for different conditions, update diagnostic accuracy with new information, and model relationships between lifestyle factors and health outcomes. The real power comes from recognizing that beneath the surface level differences in terminology and application, the same fundamental statistical patterns appear repeatedly. Once you develop this integrated system of statistical thinking, you can approach unfamiliar problems with confidence, recognizing which core concepts apply even in new domains. So why do so many professionals struggle with applying statistics to real-world data problems? The answer lies in a fundamental misunderstanding of how statistical expertise develops. Many focus on learning as many individual techniques as possible, accumulating a catalog of tests and methods, without developing the deeper statistical thinking that connects them. They know which buttons to push in statistical software, but lack the conceptual understanding to know when and why to use different approaches. This technique-focused approach creates several problems. First, it's overwhelming. There are simply too many individual methods to memorize. Second, it's brittle. When faced with a scenario that doesn't perfectly match the examples they've seen before, they struggle to adapt. Third, it's inefficient. They spend time learning specialized techniques they rarely use, while missing opportunities to deepen their understanding of the core concepts that would serve them daily. Developing statistical thinking requires a different approach. Instead of breadth, focus first on depth in these 5 core areas. Understand not just how to calculate a confidence interval, but why it works and what it truly represents. Don't just learn the formula for Bayes' theorem, but internalize how it formalizes the process of updating beliefs with new evidence. Don't just run regression models, but develop intuition for what the coefficients mean and when the assumptions might be violated. Descriptive statistics, finding the signal in the noise. With a foundation in statistical thinking established, let's examine how this applies to your first critical challenge: summarizing data. Did you know that the same dataset can tell completely different stories depending on which statistical measure you choose? The difference between mean and median might seem academic until you realize it can be the difference between a successful business strategy and a costly mistake. Imagine you're a data analyst at a retail chain. With 50 locations across the country, your boss just dropped a massive spreadsheet on your desk containing 3 months of transaction data, over 100,000 rows, from all stores. The CEO needs insights for an investor meeting in 1 hour. Where do you even begin? Looking at raw data in this form is like trying to understand a city by examining individual grains of sand. Your eyes scan the endless rows. Transaction amounts ranging from $2.99 to $1,500, timestamps across different time zones, product categories nested within departments, customer loyalty IDs. The information overwhelms your cognitive capacity. Many analysts make the critical mistake of diving into advanced analysis before properly understanding their data's fundamental characteristics. They jump straight to complex machine learning algorithms or intricate visualization dashboards. But experienced data scientists know better. They start with descriptive statistics to get their bearings. Let's break down this retail scenario. The most basic question might be, what's our average transaction value? Calculating the mean gives you 87.54. That looks reasonable, but is it representative? This is where understanding central tendency measures becomes crucial. When you calculate the median transaction value, you find it's only $32.99. This massive difference immediately tells you something important. Your data is skewed by some very large purchases. This relationship between mean and median reveals valuable business intelligence. A few high-value transactions are pulling up your average, but most customers spend much less. This insight completely changes how you might approach customer segmentation or promotional strategies. The next layer of understanding comes from measures of dispersion, how spread out your data is. The standard deviation of transaction values is $250, which is more than twice the mean. This indicates extreme variability in purchase amounts. The interquartile range, IQR, shows that the middle 50% of transactions fall between $15.99 and $78.50, further confirming the presence of outliers pulling up the average. When you examine these outliers more closely, you discover that they're primarily from your furniture department, which naturally has higher price points than grocery or personal care items. Without descriptive statistics highlighting these patterns, you might have made the catastrophic mistake of setting uniform sales targets across departments based solely on the mean value. Distribution shape gives you the final piece of the puzzle. Your transaction data follows a right-skewed distribution with a long tail of high-value purchases. This isn't abnormal for retail, but understanding this shape helps you avoid making incorrect assumptions about what constitutes a typical transaction. Now let's apply these same concepts to the product level. Looking at one of your best-selling items, organic baby food, you notice something interesting. The mean daily sales across stores is 42 units, but there's a standard deviation of 35 units. This high variability suggests inconsistent performance. When you create a simple box plot comparing sales across regions, a pattern emerges that would have remained hidden in the raw data. Stores in the Northeast region consistently outperform others, selling 60-70 units daily, while West Coast stores average only 25 or 30 units. This regional pattern might indicate demographic differences, marketing effectiveness variations, or even placement issues within stores. The power of descriptive statistics becomes even more apparent when examining time-based patterns. A histogram of transactions by hour reveals 3 distinct peaks: morning, 7-9 a.m., lunch, 12 to 1 p.m., and evening, 5 to 7 p.m. This simple visualization immediately suggests staffing adjustments that could improve customer service during peak times. What about detecting anomalies? Your raw data includes a day where one store recorded sales 500% above its normal average. Without calculating rolling averages and standard deviations, this could be misinterpreted as an amazing sales day worth replicating. But descriptive statistics reveal it as an outlier triggered by a one-time promotional event that doesn't represent sustainable performance. The critical insight here is choosing the right descriptive statistics for the question at hand. When examining the effectiveness of a new loyalty program, looking at mean spending increases could be misleading if a few customers dramatically change their behavior, while most remain the same. The median might provide a more accurate picture of typical customer response. These same descriptive tools work remarkably well across entirely different domains. Consider patient data in healthcare settings. A hospital analyzing length of stay metrics might find that the arithmetic mean is 4.7 days, but the median is only 3 days. This difference immediately highlights the impact of a small number of patients with extended stays, perhaps indicating complications or specific conditions requiring additional attention. By examining the distribution shape of patient recovery times, healthcare providers can identify whether their interventions produce consistent outcomes or highly variable results. A bimodal distribution might suggest two distinct patient populations responding differently to treatment, a crucial insight for improving care protocols. Histograms of hospital readmission rates by day can reveal critical patterns about post-discharge complications. If readmissions spike around days 10-14, this might indicate a specific point in recovery where patients need additional support or follow-up. The deceptive nature of averages appears consistently across domains. An e-commerce site might celebrate a 3% conversion rate, seemingly excellent for their industry. But descriptive statistics broken down by traffic source might reveal that organic search visitors convert at 7%, while social media visitors convert at only 0.5%. This granular understanding enables much more effective marketing budget allocation. What's particularly powerful about descriptive statistics is that they require relatively little statistical sophistication to interpret. Box plots, histograms, and summary measures like mean, median, and standard deviation can be explained to non-technical stakeholders in minutes, yet they reveal insights that might remain buried in raw data for months. Think of descriptive statistics as compression algorithms for your brain. They reduce thousands or millions of data points into a manageable set of characteristics that human cognition can actually process. This compression isn't just convenient, it's necessary for making sense of complex information. The most common mistake analysts make isn't calculating these measures incorrectly, it's applying them inappropriately. Using means for skewed data, ignoring outliers that contain vital information, or failing to examine distribution shapes can all lead to fundamentally wrong conclusions. Visual representations transform these abstract numbers into intuitive patterns. A box plot instantly communicates median, quartiles, and outliers. A histogram shows distribution shape, modality, and concentration. These visual tools bridge the gap between raw numbers and human understanding, making patterns immediately apparent that might take hours to detect in tabular data. Inferential statistics. Making decisions with incomplete information. Those visual tools illuminate the patterns in our existing data, but what about the vast universe of information we'll never directly observe? This is where the true challenge of statistics begins. Many companies base multi-million-dollar decisions on samples representing less than 1% of their total customer base. The science of making reliable leaps from what we know to what we don't is what separates statistical thinking from mere number crunching. Consider a scenario at TechFlex, a software company developing a new user interface for their flagship product. Their current active user base stands at 2.3 million people worldwide. The product team is facing a critical decision, implementing a complete interface redesign that would cost $1.8 million to develop and deploy. Before committing to this investment, they want to test if users actually prefer the new design. The challenge? Testing with all 2.3 million users is impossible. It would defeat the purpose of validating before building. Instead, they randomly select 2,500 users, roughly 0.1% of their customer base, to participate in a limited trial. Half experience the current interface, while half test the redesigned version. After 2 weeks, the data shows that users of the new interface spent 12% more time in the application and completed 8% more tasks. Sounds promising, but can TechFlex trust these results? This small sample represents just a tiny fraction of their user base. What if these 2,500 users happen to be unusually receptive to change? What if the improvements weren't due to better design, but simply the novelty effect of trying something different? This is where inferential statistics becomes indispensable. Unlike descriptive statistics, which helps us understand what our data contains, inferential statistics allows us to extend insights beyond our sample to the broader population. It provides mathematical tools to quantify the uncertainty inherent in this leap. At the heart of inferential statistics lies the concept of sampling distributions. When we take random samples from a population, the statistics from these samples, like means or proportions, form their own distribution. The remarkable property of these sampling distributions is described by the central limit theorem, one of the most profound concepts in statistics. It tells us that regardless of the original population's distribution shape, the distribution of sample means will approximate a normal distribution as sample size increases. This property allows TechFlex to calculate the probability that their observed 12% increase in engagement represents a real improvement rather than random chance. Even with just 0.1% of users, they can make reliable inferences about how all 2.3 million users would likely respond. To formalize this process, TechFlex employs hypothesis testing. They begin by stating two competing hypotheses. The null hypothesis, H0, that the new interface produces no difference in user engagement, and the alternative hypothesis, H1, that the new interface increases engagement. The null hypothesis serves as the default assumption, the status quo position that must be overthrown with convincing evidence. Through statistical analysis, they calculate a p-value of 0.03. This number represents the probability of observing a 12% increase, or greater, in engagement if the null hypothesis were true, if the new interface actually had no effect. Such a small p-value indicates strong evidence against the null hypothesis. But here's where many analysts go wrong. This p-value doesn't tell TechFlex the probability that their new interface is better. It's not the probability that the null hypothesis is true. This is a common misinterpretation that leads to costly mistakes. What the p-value actually provides is the strength of evidence against the null hypothesis, not the probability of the hypothesis itself. Similarly, TechFlex must avoid another common error, assuming that their small p-value indicates a large effect size. The p-value tells us nothing about the magnitude of the improvement. It only measures evidence against the null hypothesis. A tiny but consistent improvement can produce a very small p-value with a large enough sample. To complement hypothesis testing, TechFlex calculates confidence intervals. Their analysis shows that the true increase in user engagement likely falls between 7% and 17%, 95% confidence interval. This range provides critical business context that a p-value alone cannot offer. It tells them not just that the improvement is statistically significant, but also gives them a range of plausible values for the actual improvement. The risk of error still exists. TechFlex sets their significance level at 0.05, meaning they're willing to accept a 5% chance of a type 1 error, implementing the new design when it actually offers no improvement. They also consider the possibility of a type 2 error, rejecting a truly beneficial redesign. These aren't just statistical concepts, but represent real business risks with financial implications. This same inferential framework extends far beyond software development. Consider A/B testing, where tech companies routinely employ these methods to compare two versions of a product. When a company tests different website layouts to identify which leads to higher conversion rates, they're relying on the same statistical foundations that TechFlex used. The consequences of ignoring proper inferential methods can be severe. In healthcare, clinical trials that fail to account for sample size and variability might lead to approving ineffective or even harmful treatments. Several historical cases demonstrate how statistical errors in medical research have caused real harm to patients. Manufacturing companies use inferential statistics for quality control, testing small batches to make inferences about entire production runs. Financial institutions employ these methods to assess investment risks based on limited historical data. Marketing teams use them to forecast campaign performance before full-scale launches. What makes inferential statistics so powerful is its ability to quantify uncertainty itself. When TechFlex finally decides to implement their new interface design, they do so with a clear understanding of both the potential benefit and the statistical confidence in that estimate. Rather than making decisions based on gut feeling or limited anecdotal evidence, they've employed a rigorous framework that acknowledges uncertainty while still enabling forward progress. However, it's important to recognize that inferential statistics isn't magic. It can't turn bad data into good insights. The quality of inferences depends critically on how the sample was selected. If TechFlex had tested their new interface only with power users or only with new customers, the results wouldn't generalize to their entire user base, regardless of statistical significance. The framework also relies on probability theory to function. Without understanding the probabilistic foundations of sampling, confidence intervals, and hypothesis tests, analysts risk misinterpreting results and making flawed recommendations. Every statistical inference involves probability statements. If we repeated this sampling process many times, then in 95% of those samples, the true parameter would fall within our confidence interval. Probability, the language of uncertainty. Probability theory isn't just a foundation for statistical inference. It's the mathematical language we use to navigate uncertainty itself. What happens in your mind when you hear that a medical test is 99% accurate versus when a meteorologist predicts a 30% chance of rain? Most of us have intuitive reactions to these percentages, but those intuitions frequently lead us astray when making critical decisions with data. The human brain wasn't designed to naturally process probability. We evolved to make quick judgments based on limited information, which served our ancestors well when avoiding predators, but creates serious problems when analyzing complex data. This disconnect explains why even seasoned professionals struggle with applying probabilistic reasoning consistently. Take our opening question: what's the difference between a 10% chance of rain tomorrow and a 10% chance of a stock market crash next month? Mathematically, they're identical, 1 in 10, but our interpretation and response to these probabilities differ dramatically. With rain, we understand the prediction comes from historical weather patterns on similar days. With the market crash, the probability reflects a complex assessment of economic factors that doesn't repeat under identical conditions. This highlights how probability takes on different meanings depending on context. Probability actually has 3 main interpretations that shape how we apply it. The classical interpretation defines probability as the ratio of favorable outcomes to total possible outcomes, like calculating that rolling a 6 on a fair die has a 1/6 probability. This works well for idealized scenarios with equally likely outcomes, but breaks down in most real-world situations. The frequentist interpretation views probability as the long-run frequency of an event over many trials. If we flip a coin thousands of times and get heads 51% of the time, the frequentist would say the probability of heads is 0.51. This approach requires repeatable experiments under identical conditions, something rarely possible with business data. The Bayesian interpretation treats probability as a degree of belief that can be updated with new evidence. This allows us to incorporate prior knowledge and continually refine our understanding, perfect for dynamic business environments where conditions constantly change. These different interpretations aren't just theoretical distinctions. They fundamentally change how we approach data analysis problems and the conclusions we can legitimately draw from our results. One of the most powerful yet frequently misunderstood concepts in probability is conditional probability, the likelihood of an event occurring given that another event has already occurred. In customer behavior analysis, this becomes critical. For example, when analyzing purchase patterns, we might find that 35% of all customers buy product A and 40% of customers buy product B. But what's the probability a customer buys product A given they've already purchased product B? This conditional relationship reveals whether products complement each other or compete for the same purchase. Failing to account for these conditional probabilities can lead to incorrect assumptions about customer preferences, resulting in ineffective marketing strategies that target the wrong segments or bundle products inappropriately. The confusion often stems from a fundamental misunderstanding about independence versus dependence in probability. Two events are independent if the occurrence of one doesn't affect the probability of the other. When events are dependent, the probability of one event changes based on whether the other event occurred. Many data scientists unconsciously assume independence when analyzing multiple factors, which can lead to serious errors. In finance, for example, risk assessment models famously failed during the 2008 financial crisis, partly because they assumed independence between different investment types that turned out to be highly correlated during market stress. The models predicted portfolio risks based on historical performance of individual assets, not accounting for how these assets might move together under extreme conditions. This misunderstanding extends to analyzing customer purchase data. A marketing team might observe that customers who buy premium coffee also frequently purchase organic milk. A naive analysis might suggest these purchases are independent, leading to separate marketing strategies. However, recognizing the dependence between these purchases, perhaps both reflect a preference for high-quality food products, could inspire bundled promotions that significantly outperform separate campaigns. Another layer of probability that shapes data analysis involves probability distributions, which model how random variables behave. Different distributions represent different types of real-world phenomena. The normal distribution, with its characteristic bell curve, appears in quality control processes where natural variation clusters around a central value. Understanding this distribution helps manufacturers set reasonable tolerance limits and identify when processes drift out of control. The binomial distribution applies to scenarios with fixed numbers of independent trials, each with the same probability of success, perfect for modeling marketing campaign responses where each customer either converts or doesn't. A clothing retailer might use this distribution to predict how many customers from a sample of 10,000 will respond to a promotion with a historically observed 2.3% response rate. The Poisson distribution proved invaluable for modeling the number of events occurring within fixed intervals of time or space. Retail businesses use this to optimize staffing by modeling customer arrivals per hour. A coffee shop might analyze that customer arrivals follow a Poisson distribution with an average of 42 customers per hour, between 7 to 9 a.m., but only 15 per hour from 2 to 4 p.m., allowing them to schedule staff accordingly. Understanding which distribution applies to your data isn't just academic, it fundamentally shapes what questions you can answer and how accurately you can predict outcomes. For example, if customer purchase amounts follow a heavily skewed distribution rather than a normal one, traditional forecasting methods may systematically underestimate revenue volatility, leading to poor inventory decisions. Even with solid understanding of these concepts, experienced analysts still fall into common probability traps. The base rate fallacy occurs when we focus on specific information while ignoring relevant background rates. Consider a fraud detection system that's 99% accurate at identifying fraudulent transactions. Impressive, right? But if only 0.1% of all transactions are actually fraudulent, most flagged transactions will be false positives, a counterintuitive result that trips up even experienced analysts. The conjunction fallacy represents another persistent error, where people judge the probability of two events occurring together as more likely than one of those events occurring alone. When analyzing customer segments, an analyst might believe the probability of a customer being both female and interested in fitness products is higher than the probability of being interested in fitness products alone, a logical impossibility. These fallacies persist because our intuitive thinking about probability conflicts with mathematical reality. We naturally look for patterns and causal relationships even when confronted with random processes. This tendency leads us to see meaningful connections, in coincidental data and misinterpret statistical noise as significant trends. Bayesian thinking, updating beliefs with evidence. While traditional statistics often treats probability as fixed and objective, the real world rarely operates with such certainty. What happens when we need to make decisions with limited data and then adapt as new information arrives? That's where Bayesian thinking enters the picture, offering a mathematical framework that mirrors how humans naturally learn, and it's revolutionizing fields from medical diagnostics to artificial intelligence. Consider Dr. Chen, an emergency physician evaluating a 45-year-old patient with chest pain. Before running any tests, she knows that about 15% of patients with these symptoms actually have a heart attack. This represents her prior probability, an initial belief based on existing knowledge before seeing new evidence. When the patient's first blood test comes back positive for cardiac enzymes, Dr. Chen needs to update her assessment. The test is 90% accurate at detecting heart attacks, but also gives false positives in 20% of patients without heart attacks. Traditional statistics might simply report the test's accuracy rates, leaving the doctor to interpret what this means for this specific patient. But Bayesian thinking provides a systematic way to combine the prior probability with this new evidence to calculate a posterior probability, the updated likelihood that the patient is having a heart attack given the positive test result. This is where Bayes' theorem comes in. It's expressed mathematically as PAB equals PBA XPA PB, where PAB is the probability of event A given that B has occurred, PBA is the probability of B given A, PA is the prior probability of A, and PB is the probability of B. In our medical example, Dr. Chen can calculate that, given the positive test result, the patient now has approximately a 43% chance of having a heart attack, higher than the initial 15%, but not as definitive as the test's 90% accuracy might suggest. What makes Bayesian thinking different from traditional approaches is this explicit incorporation of prior knowledge and continuous updating as new evidence arrives. If a second test comes back positive, Dr. Chen can use her updated 43% probability as the new prior, perform another Bayesian calculation, and get an even more refined assessment. This approach aligns with how humans naturally learn. We don't approach new situations as blank slates. We bring our existing knowledge and expectations, then adjust them based on what we observe. Bayesian statistics transforms this intuitive process into mathematical precision. The applications of this thinking extend far beyond medicine. Every time you open your email inbox, Bayesian methods are silently at work. Spam filters use Bayesian updating to classify messages, learning from the frequency of certain words appearing in emails you've previously marked as spam or legitimate. As new spam techniques emerge, these filters adapt automatically, improving their accuracy by continuously updating their probability assessments for each incoming message. Similar principles power the recommendations you receive while browsing Netflix. The system begins with prior knowledge about viewing patterns across their user base, then updates its understanding of your preferences as you watch and rate content. Each new data point, whether it's completing a series, abandoning a movie midway, or giving a thumbs up, helps the Bayesian model refine its predictions about what you might enjoy next. What makes these systems so effective is their ability to handle uncertainty and adapt to changing conditions, rather than making rigid predictions based on fixed probabilities. Bayesian models maintain distributions of possibilities that evolve with new evidence. This adaptability is particularly valuable in business forecasting. Traditional forecasting methods often struggle when historical patterns shift due to market changes or when data is limited. Bayesian approaches allow analysts to incorporate domain expertise as priors, then systematically adjust forecasts as sales data comes in. If early holiday sales differ from expectations, a Bayesian model can rapidly recalibrate predictions for the remainder of the season, while traditional models might cling to outdated patterns. A powerful feature of Bayesian analysis is the concept of conjugate priors, which simplifies the mathematical complexity of updating probabilities. By choosing prior distributions from certain mathematical families, the resulting posterior distributions follow the same mathematical form, making calculations more tractable. This technical advantage enables practical implementation of Bayesian methods in complex real-world scenarios where computational efficiency matters. Another advantage of Bayesian thinking is its effectiveness with small datasets. Traditional methods often require large samples to produce reliable results, but Bayesian approaches can deliver useful insights, even with limited data, by leaning more heavily on prior knowledge when evidence is sparse. As more data accumulates, the impact of the prior gradually diminishes while the influence of the observed evidence grows. Google leverages Bayesian methods extensively in its decision-making processes. When optimizing ad placements or refining search algorithms, their systems continuously update probability estimates based on user interactions. This allows them to balance exploration, trying new options that might work better, with exploitation, sticking with what's known to work well. A classic problem in machine learning that Bayesian approaches are particularly well suited to address. The contrast with traditional statistical methods becomes most apparent when dealing with sequential decision-making. Consider a case study from medical diagnostics where doctors needed to determine the effectiveness of a new treatment. A traditional approach might require recruiting a large sample of patients and waiting until all results were collected before drawing conclusions. A Bayesian analysis, however, allowed for continuous evaluation as each patient's outcome became available. This enabled earlier identification of effectiveness patterns, potentially saving lives by accelerating the adoption of beneficial treatments or the discontinuation of harmful ones. The power of Bayesian thinking also shines in how it handles conditional dependencies. Traditional methods often make simplifying assumptions about independence between variables that don't hold in complex, real-world scenarios. Bayesian networks explicitly model these dependencies, creating more accurate representations of how different factors influence each other, critical in fields like risk assessment, where interconnections between variables can create cascading effects. Perhaps the most profound impact of Bayesian thinking is philosophical. It shifts our perspective from treating probability as an inherent property of the world to viewing it as a reflection of our state of knowledge. Probabilities aren't fixed. They evolve as we learn more. This viewpoint acknowledges that different observers with different information may reasonably hold different beliefs, while providing a framework for converging toward agreement as shared evidence accumulates. This perspective is particularly valuable when navigating controversial or emotionally charged topics. Rather than framing disagreements as conflicts between right and wrong, Bayesian thinking suggests we simply have different priors and have been exposed to different evidence. This creates space for updating beliefs rather than defending positions, potentially reducing polarization in public discourse. Regression analysis, predicting outcomes, and understanding relationships. From updating beliefs about what has happened, we now turn to predicting what will happen next. In an era of neural networks and advanced computational methods, companies from Fortune 500 giants to small startups still rely heavily on a statistical technique developed in the early 1800s. This mathematical approach isn't just surviving, it's thriving as an essential tool across virtually every industry where prediction matters. When a retail executive needs to forecast next quarter's sales, or when a healthcare administrator wants to understand what factors most influence patient recovery times, they turn to the same fundamental technique: regression analysis. This approach serves as a bridge between simply understanding relationships in data and actually making predictions that drive decisions. Consider what happens when you try to determine which factors truly influence an outcome versus those that merely correlate with it. The human mind naturally seeks patterns, often leading us to identify connections that don't represent genuine causal relationships. This is where regression analysis provides structure to our thinking, helping separate signal from noise in complex datasets. A national retail chain recently faced this exact challenge. With sales data flowing in from hundreds of locations, they needed to understand which factors were actually driving revenue differences between stores. Was it location demographics, store size, product selection, marketing spend, or some combination of these factors? Through regression analysis, they identified that while all these variables showed some correlation with sales, the strongest predictors were actually store visibility from main roads and the experience level of the store manager. This example highlights the power of regression analysis as not just a predictive tool, but an explanatory one. The model didn't simply predict which stores would perform better, it quantified exactly how much each factor contributed to the outcome, allowing executives to make targeted improvements rather than changing everything at once. At its core, regression analysis works by finding the mathematical relationship between one or more independent variables, like marketing spend or store location, and a dependent variable, like sales. In its simplest form, linear regression, this relationship is represented as a straight line that minimizes the distance between itself and all the actual data points. The beauty of this approach lies in its interpretability. Each independent variable gets assigned a coefficient that tells you exactly how much the outcome changes when that variable increases by 1 unit, holding all other variables constant. This direct mapping from input to impact is why regression remains indispensable, even as more complex black box machine learning algorithms have emerged. For example, a coefficient of 2.5 on marketing spend, measured in thousands of dollars, would mean that for every additional $1,000 spent on marketing, we expect sales to increase by $2,500, assuming nothing else changes. That kind of clear, quantifiable insight is extraordinarily valuable for decision makers who need to justify investments and prioritize actions. But regression is far more than just drawing lines through data points. Multiple regression allows analysts to consider many variables simultaneously, controlling for confounding effects and isolating the unique contribution of each factor. This helps address the fundamental challenge of correlation versus causation by accounting for the complex interplay between variables. More sophisticated diagnostic tools help identify when a regression model's assumptions are violated, potentially leading to incorrect conclusions. For example, the assumption that relationships between variables are linear may not hold in real-world scenarios. When this happens, analysts can employ variations like polynomial regression to capture more complex relationships. When a retailer ran a regression analysis on their historical sales data, they discovered that adjusting their inventory based on the model's predictions led to a 15% increase in revenue. This impressive result didn't come from complicated artificial intelligence. It came from the careful application of a 200-year-old statistical technique that provided clear, actionable insights. What makes regression particularly powerful is how it extends beyond simple linear relationships. When predicting binary outcomes like whether a customer will purchase a product or not, logistic regression transforms the linear model into probability estimates between 0 and 1. For time-based patterns, time series regression incorporates seasonal effects and trends. For data with natural hierarchies, multi-level models capture variations at different scales of analysis. This versatility explains why regression analysis forms the backbone of predictive work across diverse fields. In finance, regression models help determine which economic indicators most influence stock prices. In healthcare, they predict patient outcomes based on treatment variables and demographic factors. Environmental scientists use regression to understand how different pollutants affect ecosystem health. Marketing teams employ it to optimize advertising spend across different channels. Interestingly, when comparing simple linear regression against more complex machine learning approaches, research has found that while machine learning might provide marginally better accuracy in some cases, regression models often prove sufficient for many business applications. Their interpretability and ease of implementation make them particularly valuable when explanations matter as much as predictions. This doesn't mean regression is without challenges. One common pitfall occurs when analysts fail to check for multicollinearity. When independent variables are highly correlated with each other, this can inflate the variance of coefficient estimates and make the model unreliable, potentially leading to incorrect business strategies based on flawed interpretations of the data. Another challenge involves mistaking correlation for causation even within a regression framework. A model might show a strong relationship between ice cream sales and drowning incidents, but the underlying cause is likely the summer season influencing both variables, not one causing the other. This is why thoughtful variable selection and domain knowledge remain essential companions to statistical technique. What truly sets regression apart is how it balances predictive power with explanatory clarity. Unlike many advanced machine learning algorithms that function as black boxes, regression models provide transparent insights into how and why predictions are made. This transparency builds trust with stakeholders and enables more informed decision-making. Consider a healthcare administrator trying to reduce patient readmission rates. A complex neural network might predict readmissions with slightly higher accuracy, but would offer little explanation about which factors drive those readmissions. A regression model, while perhaps slightly less accurate in its predictions, would clearly identify that factors like medication adherence, follow-up appointment attendance, and access to transportation explained most of the variation in readmission rates, insights that immediately suggest specific interventions. The enduring value of regression also stems from its mathematical foundation. The method systematically minimizes prediction errors, finding the optimal model parameters that best fit the data. This optimization approach forms the conceptual foundation for many more advanced techniques in machine learning and artificial intelligence. Understanding regression isn't just about mastering a specific technique. It's about developing a way of thinking about relationships in data. This framework helps analysts approach new problems by first identifying potential predictor variables, then systematically testing their influence on outcomes of interest. As data becomes increasingly abundant and complex, the value of regression only grows. Rather than being replaced by newer methods, regression serves as the foundation upon which more sophisticated analyses are built. Many advanced machine learning approaches can be understood as extensions or generalizations of the core regression framework. Statistical biases, the hidden traps in data analysis. As powerful as regression and other statistical methods are, they remain tools wielded by human minds, vulnerable to systematic errors in thinking. Even the most sophisticated analysis in the world becomes useless when viewed through the lens of biased judgment. Our minds don't just occasionally make random errors, they fall into predictable patterns of flawed reasoning that can completely invert the meaning of perfectly valid statistical results. Consider this scenario. A pharmaceutical company conducts a meticulously designed clinical trial, employs appropriate statistical methods, and concludes their new drug is effective. The numbers check out perfectly. Yet months later, when the drug is used more widely, it proves far less effective than the trial suggested. What happened? The statistical calculations were flawless, but human bias had silently shaped which patients were selected for the trial, which outcomes were measured, and which results were deemed worthy of publication. The uncomfortable truth is that even when our statistical techniques are applied correctly, our cognitive architecture can sabotage our conclusions. These aren't random errors, but systematic patterns in how we process information, evaluate evidence, and form judgments. The most dangerous aspect, these biases operate largely outside our conscious awareness. Take confirmation bias, our tendency to favor information that confirms pre-existing beliefs while disregarding contradictory evidence. A marketing analyst might run dozens of tests on customer data, but unconsciously focus only on the results that support their initial hypothesis about customer behavior. The statistical methods themselves aren't flawed, but the selective attention to certain results creates a distorted picture of reality. This phenomenon extends beyond individual analysts to entire organizations. Consider a tech company that implemented a new recommendation algorithm. initial metrics showed a 5% increase in user engagement, confirming executives' beliefs in the new approach. However, deeper analysis revealed that while engagement rose for some user segments, it actually decreased significantly for others. The company had fallen victim to confirmation bias by focusing exclusively on the metrics that validated their existing beliefs about the algorithm's effectiveness. Sampling bias presents another insidious trap. When our data doesn't represent the population we're trying to understand, even perfect statistical analysis leads to fundamentally flawed conclusions. Imagine a survey on public opinion conducted only among urban professionals between ages 25 to 40. The statistical analysis might be mathematically sound, but the results will present a skewed picture of public sentiment that excludes rural populations, older generations, and other demographic groups. This bias has profound real-world consequences. Medical research has historically suffered from sampling bias, with clinical trials often overrepresenting certain demographics while underrepresenting others. The result? Treatments that work well for the populations included in studies may prove ineffective or even harmful for those who weren't adequately represented. Survivorship bias creates perhaps the most deceptive statistical illusions. By focusing only on successful cases and ignoring failures, this bias generates overly optimistic conclusions about strategies, investments, and performance. Consider an investment firm analyzing the returns of currently traded stocks over the past decade. Their analysis shows impressive average returns, but completely misses the stocks that performed so poorly they were delisted from exchanges. The statistical calculations are correct, but they're being performed on a dataset that systematically excludes failures. This bias appears regularly in business case studies that examine successful companies to extract winning strategies. By ignoring companies that used similar strategies but failed, these analyses attribute success to factors that may actually be irrelevant or even detrimental. The statistics themselves don't lie, but they're being asked questions about an incomplete picture of reality. Anchoring effects further distort our interpretation of statistical results. When an initial value or benchmark influences our judgment of subsequent information, we've been anchored. A sales forecast that begins with last year's numbers as a baseline might systematically underestimate growth potential in rapidly expanding markets. The statistical models work correctly, but the anchoring effect subtly constrains how we interpret and apply the results. Even the framing of statistical findings, how results are presented and contextualized, can dramatically alter their interpretation and impact. Consider two ways of presenting the same healthcare statistic. The treatment improves survival rates by 50% versus the treatment increases 5-year survival from 2% to 3%. Both statements are statistically accurate, but they create vastly different impressions and likely lead to different decisions. These biases don't just affect novices, they can impact experienced data scientists and statisticians. In fact, expertise sometimes breeds overconfidence, making professionals less likely to question their interpretations or seek disconfirming evidence. So, how can we guard against these invisible cognitive traps? Awareness alone isn't enough. Research shows that simply knowing about biases doesn't prevent us from falling prey to them. Instead, we need systematic countermeasures built into our analytical workflows. One powerful approach is implementing blind analysis techniques, where analysts don't know the expected outcomes or even which variables represent which concepts. This approach, borrowed from physics research, prevents our expectations from influencing how we process and interpret data. When an analyst doesn't know which treatment group received the actual intervention versus the placebo, they can't unconsciously favor analyses that show the expected effect. Diverse analytical teams provide another layer of protection. When team members bring different perspectives, assumptions, and prior beliefs to the table, biases that might go unnoticed by individuals become visible through group discussion. A team with varied backgrounds is more likely to question assumptions, consider alternative hypotheses, and identify potential biases before they contaminate conclusions. Pre-registration of analytical plans represents a particularly effective safeguard against many cognitive biases. By specifying exactly which analyses will be conducted before looking at the data, researchers prevent themselves from selectively choosing analyses that yield desired results. This approach forces accountability to the original research questions rather than allowing a drift toward whatever the data seems to suggest. Statistical training that emphasizes bias recognition proves invaluable. Understanding principles like random sampling helps analysts implement techniques that minimize sampling bias. When analysts understand how various biases manifest in data collection and analysis, they can design studies and analyses specifically to counteract these tendencies. Consider this example of bias mitigation in action. A retail company wanted to understand why certain store locations outperformed others. Their initial analysis focused exclusively on the characteristics of high-performing stores, a classic survivorship bias approach. After recognizing this bias, they redesigned their analysis to include all stores, specifically comparing successful and unsuccessful locations with similar characteristics. This complete picture revealed that factors they initially attributed to success, like premium locations, were actually less important than operational variables they had overlooked. Forward-thinking organizations are now implementing structured analytical processes specifically designed to combat cognitive biases. These include adversarial analysis, where team members are assigned to actively look for problems with proposed interpretations, and routine sensitivity analyses that test how results change under different assumptions. By institutionalizing skepticism and alternative viewpoints, these approaches help prevent bias-driven misinterpretations. The most important step in overcoming these biases is acknowledging that statistical expertise alone doesn't protect us from cognitive traps. Even the most sophisticated statistical knowledge can't compensate for biased data collection, selective analysis, or skewed interpretation. True statistical thinking requires not just technical mastery, but metacognitive awareness, the ability to think critically about our own thinking. Data visualization, making statistics meaningful. Statistical fluency requires more than just mastering analytical techniques. It demands the ability to communicate insights effectively. Even the most brilliant statistical analysis remains useless if decision-makers can't understand its implications. Organizations frequently face a critical disconnect between analytical findings and actionable decisions. Consider what happens when data scientists present their meticulous work to executives or clients who lack technical backgrounds. All too often, those complex statistical tables, dense spreadsheets, and jargon-heavy explanations fail to translate into meaningful comprehension. I once consulted with a mid-sized retailer that had invested heavily in customer analytics. Their data team had uncovered significant patterns showing how certain product combinations drove increased basket size. The findings could have transformed their merchandising strategy and potentially increased revenue by 18%, but when presented as a multi-page statistical report filled with correlation coefficients and confidence intervals, the executive team glazed over. The insights went unused for months until someone finally translated those numbers into visual stories showing clear product relationships and sales potential. This scenario plays out constantly across industries. A healthcare system might miss critical patterns in patient readmission rates because they're buried in spreadsheets. Marketing teams may overlook emerging customer segments because the clustering analysis appears only as numerical outputs. Financial institutions might fail to spot emerging risks despite having all the necessary data right in front of them. The challenge isn't data collection or even analysis, it's effective communication through visualization. The human brain processes visual information approximately 60,000 times faster than text. A well-crafted visualization can make complex statistical patterns immediately apparent even to those without formal training in statistics. When working with statistical data, choosing the right visualization format is crucial. Different statistical concepts demand different visual representations. Bar charts work brilliantly for comparing categorical data, allowing viewers to quickly identify the highest and lowest values across groups. Histograms reveal the shape and distribution of continuous data, making it easy to spot whether values cluster around a central point or spread across a wide range. Scatter plots reveal relationships between variables that might remain invisible in tabular data. They instantly show patterns like linear trends, clusters, or outliers that would be nearly impossible to identify from numbers alone. Line charts excel at displaying change over time, revealing trends, seasonality, and potential inflection points in longitudinal data. The transformation from raw statistical output to effective visualization can be dramatic. Imagine a dataset showing customer purchase patterns across 50 retail locations. When presented as a table of numbers, identifying patterns requires intense concentration and mental effort. But visualize that same data as a heat map, where color intensity represents purchase frequency, and suddenly geographic patterns leap into view, making it immediately clear which regions outperform others. Let me share a particularly telling example. A financial services company had been tracking customer retention rates across different demographic segments for years. Their quarterly reports included dozens of tables showing retention percentages by age group, income level, and account type. Despite having all this information, executives couldn't easily identify which segments were problematic. When those same statistics were transformed into a simple tree map visualization, where box size represented segment size and color represented retention rate, the problem areas became immediately apparent. Areas of bright red, poor retention, in large boxes, important segments, demanded immediate attention, leading to targeted initiatives that improved overall retention by 12%. Visualization choices can either reveal or obscure important patterns in the same dataset. Consider a time series showing monthly sales data that includes a significant but brief spike during a promotion period. A line chart with an appropriately scaled y-axis would clearly show this spike, drawing attention to the promotion's effectiveness. But if the y-axis starts at 0, when all values fall between 80 and 100, the variation becomes nearly invisible, potentially leading decision-makers to conclude the promotion had minimal impact. The difference between an ineffective and effective visualization often comes down to design choices that prioritize clarity over complexity. A cluttered visualization with too many variables, unnecessary decorative elements, or confusing color schemes can hide the very insights it's meant to reveal. Effective visualizations follow principles of simplicity, using color purposefully to highlight important patterns, eliminating extraneous details, and providing clear titles and labels that guide interpretation. Interactive visualizations take communication a step further by allowing stakeholders to explore statistical relationships themselves. Rather than presenting a single static view of the data, interactive tools let users filter information, drill down into specific segments, or change variables to answer their own questions. This exploration builds deeper understanding and trust in the underlying statistical analysis. For instance, an interactive dashboard showing customer behavior might allow marketing directors to filter by demographic characteristics, purchase categories, or time periods. As they interact with the data, noticing how different segments respond to various marketing approaches, they develop intuitive understanding of the statistical patterns that would be difficult to achieve through static reports alone. One of the most challenging aspects of statistical communication involves conveying uncertainty, a concept fundamental to statistical thinking, but often misunderstood by non-specialists. Visualizing uncertainty helps prevent the common mistake of treating statistical estimates as exact values. Error bars represent confidence intervals on graphs, providing visual cues about the reliability of each estimate. Shaded regions under curves can indicate variability in the data, helping viewers understand where predictions are more or less certain. These visual techniques transform abstract concepts like confidence intervals into intuitive visual elements that non-statisticians can grasp without understanding the underlying mathematics. When displaying distributions, density plots and histograms allow viewers to see the shape of the data, revealing important characteristics like skewness or multiple peaks that might indicate distinct subgroups. A single histogram can instantly communicate whether data is normally distributed or follows some other pattern, information that might take paragraphs to explain in text. Correlation between variables comes alive in scatter plots, where viewers can immediately see not just whether a relationship exists, but its nature and strength. Clusters of points, linear trends, and outliers all become visible at a glance, enabling quick identification of patterns that might otherwise require sophisticated analysis to detect. The difference effective visualization makes cannot be overstated. In one striking case, a company's data scientists had been tracking market signals for months using complex statistical tables. The analysis showed clear warning signs of changing customer preferences, but when presented as dense numerical data, executives couldn't perceive the urgency. The key insights remained buried until someone created a simple visualization showing the diverging trend lines. What had been a $2 million oversight could have been prevented with a single well-designed chart. This pattern repeats across industries and applications. Environmental researchers might struggle to communicate complex climate models until visualization transforms abstract projections into compelling visuals. Public health officials can more effectively communicate risk when statistical probabilities are represented through visual metaphors that resonate with the public. Economic forecasts become more actionable when uncertainty is visually represented rather than buried in footnotes about confidence intervals. The most effective statistical visualizations transform complex concepts into visual patterns that humans can process intuitively. They map abstract numbers to visual properties like position, size, shape, and color that our brains have evolved to process effortlessly. This translation from mathematical abstraction to visual pattern is what enables non-specialists to grasp statistical insights without needing to understand the underlying calculations. The statistical thinking framework, choosing the right tool. That translation from mathematical abstraction to intuitive understanding is powerful, but it assumes we've selected the correct statistical tool from the start. Choosing the right statistical approach is where many analysts stumble, regardless of their experience level. According to research, a significant portion of analytical errors stem not from calculation mistakes, but from applying an inappropriate statistical test to the question at hand. The difference between insightful analysis and misleading conclusions often comes down to this critical decision at the very beginning of the analytical process. Imagine you've collected customer satisfaction data for your product. Should you run a t-test to compare satisfaction between two customer segments? A chi-square test to examine categorical relationships? Or perhaps a regression analysis to identify which factors most strongly predict satisfaction levels? Each approach answers fundamentally different questions, and choosing incorrectly can lead you down an analytical rabbit hole that wastes time and potentially delivers misleading conclusions. This challenge becomes particularly evident when we look at real-world analytical missteps. Consider a marketing team that employed a sophisticated multivariate analysis to determine which factors influence customer retention, only to discover later that a simple chi-square test would have provided clearer insights with less effort. Or the healthcare researchers who initially used complex regression models when testing a straightforward hypothesis about treatment effectiveness, where a t-test would have been sufficient and more interpretable for their stakeholders. What we need is a structured framework, a decision tree of sorts, that helps analysts match the right statistical tool to the specific question at hand. This framework starts with understanding the fundamental question your analysis seeks to answer. Are you trying to describe what happened? Infer whether an observed difference is statistically significant. Predict future outcomes? or update your understanding based on new evidence. Let's break down how this decision framework might look in practice. When your primary goal is to understand and summarize data characteristics, descriptive statistics naturally become your first choice. This approach is particularly valuable during exploratory data analysis when you're getting familiar with a new dataset. The framework would direct you toward measures of central tendency and dispersion, along with visualizations that help identify patterns, outliers, and distribution shapes. When your question involves making inferences about a broader population based on sample data, the framework guides you toward inferential statistics. But it doesn't stop there. It helps you select the specific inferential test based on your data characteristics. When population standard deviation is known, a z-test is appropriate, while a t-test is used when it is unknown. For categorical data, a chi-square test helps assess whether observed frequencies differ significantly from expected frequencies, making it particularly valuable in fields like market research and social sciences. This decision-making becomes even more nuanced when we consider probability-based questions. If you are trying to quantify the likelihood of future events or understand dependencies between variables, probability models become essential. The framework would help you determine whether to use a binomial distribution for binary outcomes, a Poisson distribution for count data over fixed intervals, or other probability models based on your specific scenario. For questions that involve updating beliefs with new evidence, Bayesian approaches become the natural choice. And when you need to understand relationships between variables or predict outcomes, regression analysis offers a powerful and interpretable solution. But the real power of this framework lies in its ability to help analysts navigate away from analytical overkill. Case studies have consistently shown that simpler statistical approaches, such as using a t-test instead of more complex models, can yield equally valid results while being easier to interpret and communicate. For example, a study comparing the effectiveness of two teaching methods found that a straightforward t-test provided clear insights without the need for more complicated analyses. Let's see how this framework applies across different domains. In retail analytics, a question about which customer segments spend more would lead you to descriptive comparisons and possibly t-tests to determine if differences are significant. Questions about whether product placement influences purchase decisions might direct you toward chi-square tests for categorical data. And predictions about future sales based on multiple factors would naturally lead to regression analysis. In healthcare, questions about treatment effectiveness typically call for inferential methods like t-tests or ANOVA. Questions about patient risk factors might lead to logistic regression, while predictions about hospital resource needs could employ time series analysis. The framework helps healthcare analysts avoid both underpowering their analysis with overly simplistic methods and overcomplicating their approach when simpler tools would suffice. Financial analysts can use this framework to identify when descriptive statistics are sufficient for reporting current portfolio performance, when probability models are needed to quantify investment risks, and when regression analysis is appropriate for predicting market movements based on economic indicators. One critical component of this decision framework is understanding the underlying assumptions of statistical tests. Expert opinion suggests that this understanding is crucial for their correct application. For instance, the assumption of normality is vital for the validity of both z-tests and t-tests, and violations of this assumption can lead to incorrect conclusions. The framework would include checkpoints to verify these assumptions, ensuring analysts don't apply methods incorrectly. This leads us to an important principle: statistical parsimony, the practice of using the simplest statistical approach that adequately addresses the question at hand. William of Ockham's famous principle that entities should not be multiplied beyond necessity applies perfectly to statistical analysis. When simpler methods can provide valid insights, there's no need to employ more complex approaches that may introduce unnecessary assumptions, complications, or interpretive challenges. Statistical parsimony isn't about avoiding advanced methods entirely. It's about matching the complexity of your analytical approach to the complexity of your question and data. Sometimes more sophisticated techniques are absolutely necessary, particularly when dealing with hierarchical data structures, complex time series, or high-dimensional relationships. The framework helps identify these situations while preventing unnecessary analytical complexity in more straightforward scenarios. Consider a manufacturing company analyzing product defects. While machine learning algorithms might identify complex patterns in defect occurrence, a simpler analysis using control charts and basic hypothesis testing might provide equally valuable insights with greater transparency and easier implementation. The framework would guide analysts toward these simpler approaches unless the specific question or data characteristics necessitated more advanced methods. What makes this decision framework so powerful is that it focuses on the question type, data characteristics, and required confidence level, three factors that transcend domain-specific knowledge. Whether you're analyzing customer behavior, patient outcomes, financial markets, or manufacturing processes, the same core decision principles apply. Building this framework into your analytical workflow creates a structured approach that improves consistency and reliability. By explicitly considering the nature of your question, the characteristics of your data, and the required confidence level before selecting a statistical approach, you significantly reduce the risk of analytical mismatch. This process makes your analysis more defensible, more interpretable, and ultimately more valuable to decision makers. Statistical transfer learning, solving new problems with core principles. Beyond selecting the right statistical tool lies an even more valuable skill, the ability to transfer statistical thinking across domains. While most analysts become specialists in their field's specific methods, elite data scientists recognize the same statistical patterns appearing across wildly different contexts, allowing them to solve problems in industries they've never worked in before. This adaptability seems almost magical until you understand what's happening behind the scenes. Imagine a data scientist who has spent years analyzing retail customer behavior suddenly being asked to help optimize patient care in a hospital network. At first glance, these domains share little in common. One deals with products and purchases, the other with treatments and health outcomes. Yet, experienced practitioners can make this transition seamlessly by recognizing the underlying statistical similarities. What enables this cross-domain fluency? It comes down to recognizing that beneath the surface-level differences in terminology and context, many problems share fundamental statistical structures. The ability to strip away domain-specific language and identify these core patterns is what separates versatile data scientists from those confined to a single industry. Consider how healthcare systems and retail operations, despite their obvious differences, often face parallel analytical challenges. Both need to understand the distribution of key metrics, patient recovery times or customer purchase frequencies, assess the impact of interventions, treatment protocols, or marketing campaigns, and predict future behaviors, patient readmissions, or repeat purchases. The contexts differ dramatically, but the statistical frameworks remain remarkably similar. This transfer of statistical thinking begins with pattern recognition. Expert data scientists develop what we might call statistical abstraction, the ability to see past the specific details of a problem and identify its fundamental statistical structure. When approaching an unfamiliar domain, they first ask, what type of statistical question is being asked here? Is this fundamentally about understanding distributions, testing differences, modeling relationships, quantifying uncertainty, or updating beliefs? By recognizing these patterns, the data scientist can draw on their core statistical toolkit rather than domain-specific methods. They understand that whether they're examining customer churn in a subscription service or patient non-compliance with medication regimens, they're essentially dealing with the same type of time-to-event analysis. The terminology changes, but the statistical approach remains consistent. The ability to recognize patterns and apply statistical methods across different domains is what sets successful data scientists apart from their peers, notes one expert in the field. This meta-skill, the ability to abstract problems to their statistical essence, accelerates learning and problem-solving in new contexts. Let's examine a concrete example of statistical transfer learning in action. A healthcare study revolutionized patient treatment protocols by borrowing statistical methods directly from financial analysis. The researchers recognized that patient progression through different treatment stages shared statistical similarities with how financial assets move through market states. By applying time series methods typically used for financial forecasting, they were able to develop more accurate predictive models for patient outcomes, despite having no prior healthcare experience. This cross-pollination of methods demonstrates the power of seeing beyond domain boundaries. The researchers didn't need to become healthcare experts overnight, they simply needed to recognize the underlying statistical similarity between the two domains and adapt their existing tools to the new context. What makes this transfer possible is focusing on statistical patterns rather than surface-level domain differences. When approaching a new field, experienced data scientists look for familiar statistical signatures. 1. Distribution patterns. Is the data normally distributed, skewed, or multimodal? The same techniques for handling skewed sales data can be applied to skewed healthcare costs. 2. Correlation structures. How do variables relate to each other? The methods for understanding how marketing channels influence each other can be adapted to understand relationships between different health metrics. 3. Time-dependent behaviors. Does the phenomenon change over time? Time series methods work, whether you're forecasting stock prices or patient admissions. 4. Hierarchical relationships. Is there nesting in the data? Multi-level modeling approaches work for students within schools, employees within companies, or patients within hospitals. 5. Causal questions. What drives what? The frameworks for estimating causal effects apply whether you're evaluating marketing campaigns or medical interventions. By focusing on these fundamental patterns, data scientists can quickly transfer their expertise across domains without becoming specialists in each field. This doesn't mean domain knowledge is irrelevant, quite the contrary. Domain experts provide crucial context and validation. But statistical transfer learning allows data scientists to contribute meaningful insights even while they're still learning the domain. Integration between statistical thinking and domain expertise creates a powerful synergy. The statistician brings transferable analytical frameworks, while domain experts contribute contextual understanding and practical constraints. Together, they can solve problems more effectively than either could alone. Another compelling example comes from retail analytics techniques being successfully applied to optimize operations in manufacturing. The statistical methods used to analyze customer purchasing patterns were adapted to understand machine performance patterns on a factory floor. By recognizing the underlying similarity, both involve sequence analysis and pattern recognition in time series data. Analysts were able to transfer their retail analytics knowledge to improve manufacturing efficiency. How can analysts develop this transferable statistical thinking? It begins with understanding statistical concepts at a deeper level beyond memorizing formulas or technique names. Instead of learning methods as isolated tools, focus on why each method works, what assumptions it makes, and what patterns it's designed to detect. This deeper understanding creates flexible knowledge that can be adapted to new contexts. When you understand the principles behind regression analysis, not just how to run it, you can apply that understanding whether you're modeling sales figures or patient outcomes. Developing transferable statistical thinking also requires looking beyond the specific examples used to teach concepts. Statistical textbooks might demonstrate t-tests using manufacturing quality control examples, but the same principles apply to comparing treatment outcomes or website conversion rates. By mentally replacing the variables in examples with those from different domains, you can practice seeing the common patterns. cross-domain analogies also enhance transfer learning. Expert data scientists often maintain a mental library of statistical patterns they've encountered across different fields. When facing a new problem, they ask, what does this remind me of? Have I seen a similar pattern in another context? These analogies help bridge the gap between familiar and unfamiliar domains. The ability to transfer statistical thinking also helps avoid reinventing the wheel. Many industries develop specialized analytical methods without realizing similar approaches exist elsewhere. For instance, survival analysis techniques originally developed for medical research have valuable applications in customer lifetime value analysis for businesses. By recognizing these cross-domain connections, data scientists can import established methods rather than creating new ones from scratch. Integration of statistical thinking into everyday problem-solving processes allows data scientists to navigate complex datasets and derive actionable insights regardless of the industry. This abstraction skill, identifying the statistical essence of problems, provides a universal language for approaching data challenges across domains. What practical steps can analysts take to develop this transferable statistical thinking? First, study problems from multiple domains and identify their common statistical structures. Second, practice translating problems from one domain to another. Reframe a healthcare question as a retail question, and vice versa. Third, focus on understanding the why behind statistical methods rather than just the how. And fourth, collaborate with domain experts to understand the unique aspects of each field while applying transferable statistical frameworks. And this brings us to perhaps the most valuable insight of all. Statistical literacy isn't just an academic exercise. It transforms decision-making capacity. Organizations with higher statistical literacy are 2.5 times more likely to make data-driven decisions that deliver measurable results. As you continue your journey, resist the temptation to chase every new statistical technique or algorithm. Instead, deepen your understanding of these 5 core concepts we've explored. They form the foundation upon which all statistical innovation is built. Remember that beneath every complex data problem lies simple statistical patterns that repeat across domains. This universal language of uncertainty isn't limited to data science. It enhances decision-making in every aspect of life. Statistical thinking isn't about formulas or software. It's about seeing through complexity to find clarity when the path forward is uncertain.